So this one's called One More Dif EQ Topic. There might be one more in addition to this one more. So this wasn't the final one, but this was one more. The main things we're going to be doing are finding particular solutions, doing approximations, either doing slope fields, Euler's method, or linear approximations by making tangent lines. However, I have seen problems like this pop up where they say, all right, here's a differential equation. It's not separable, so we can't really do a lot with it. And then they say something about the original. They say, here's the solution right here. You're actually going to go through the work and find what makes this linear equation the solution to this. It's complicated. I think once I go through it and show you the answer, you'll see why all of this kind of fits together the way it does. Not a major topic. I don't see this a lot, but it does come up on FRQ sometimes. All right, so we know we have this differential equation. Can't separate it. 2x minus y. We could do approximation strategies, which we did in class today, but we don't know what the original equation would be. However, they're kind of giving something away, saying that the particular solution is going to deal with a linear equation. Turns out if it's linear, we can find the particular solution another cool way. So see if you can follow my logic. dy dx just means slope, right? So they're telling you the slope of your function, or, well, it is a function because it's going to be linear. Well, what is the slope of this function? If we take the derivative, we get m, right? The slope of a line is just m. So really what they're telling you is this slope needs to equal this slope. So we're going to try to form an equation together. Another thing you can do to eliminate another variable is notice that they tell you that they want y equals mx plus b to be a solution to this differential equation, which literally means y needs to work in the differential equation. So in place of y, we can substitute this particular solution they tell me that needs to work. And now I have an equation I can solve. It doesn't look like I can solve it, but watch, I can. Distribute the negative. Gather your x terms, and they already are, so I'm going to factor out an x. 2 minus m minus b equals m. All right, so here's the thing I ask about in the discussion. We've done this before, kinda. This is that thing I call equate the coefficients. So if you notice, on the left, we have an x term. On the right, we don't really have an x term. So in a way, we can think of it as 0x. Well, I need this x term and this x term to equal. So I can set the coefficient equal. On the left, I need the x term, its coefficient, to equal the coefficient on the right. In other words, m equals 2. It's a strategy called equating the coefficients. I can do the same thing with the constant. So on the right, if you notice the constant's m, on the right, the constant's negative b. So I can set those two things equal. And the benefit is I already found m to be 2. So I got b. And we've done exactly what they wanted. We have found m and b. So we know the solution is 2x minus 2. There's your particular solution. All right, so what on earth did we just do? Let me show you. Essentially what we're doing is saying, hey, here's an equation or function where this derivative is true for all of its values. Is it really true? Let's find out. If I came up with a t-chart and I talked about the derivative using this differential equation, using the very original differential equation, does it hold up? Let's pick some points like negative 1, 0, 1, 2. Should be enough to convince you. If I plug negative 1 into the solution, into the equation, I get negative 1 times 2 is negative 2 minus 2 is negative 4. If I plug in 0, I get negative 2. If I plug in 1, I get 0. If I plug in 2, I get 2. So what I am trying to convince myself of is this differential equation, does it apply to this linear function? So it's saying, okay, well, in order to get the derivative, plug in x and y to the differential equation. So 2 times our x coordinate minus our y coordinate. And what do we get? Negative 2 plus 4 is 2. So you're telling me that in this linear equation, the slope at this point is 2. And yeah, of course it is, because it's a line. So the slope is 2. How about 0, negative 2? Does it work also there? Well, if we plug in 0, negative 2, we get 2 for the slope there. If I plug in 1, 0, I get 2. If I plug in 2, 2, I get 2. So yes, this particular function, particular solution, this function is satisfied by this differential equation. This really is the derivative of this equation. And one last little check just to really convince you and hammer it home. If I plugged y into the differential equation, which you can always do that, at the end of the day, y is just all by itself in the original. If I plug it into the differential equation, I mean, what do you notice? 2x and 2x cancel, distribute, slope is 2. So this is just a really wonky way of looking at a linear equation and its slope. Really, at the end of the day, it's all it is. It's just a linear function. Slope is 2. But another way to say, oh, the slope is really to say, well, the slope is 2x minus y. And yes, the relationship between x and y makes it so that every time you plug in the xy coordinate, you always result in a slope, which is 2. Yeah, a little weird, but I've seen problems like this where they really want you to have an understanding of how differential equations work and other techniques rather than separation of variables. But the main one is separation of variables.